Right, we're back here now on this topic of path difference, and we've got our blue wave and our red wave. These have changed, so they look like people, but they're actually waves, and they're aiming for point X. We know that if these two waves start off like this, they're both equidistant from point X, and so they're going to arrive at exactly the same time, presuming they're travelling at exactly the same speed by their waves in the same medium. So they are. They're going to arrive at exactly the same time, and therefore if their arms line up here, they're going to line up over there as well. They're going to arrive in phase, crest to crest, trough to trough. And so now what we're going to think about is, what about if we have another point? Is there any other place, thinking about these as waves, that they could arrive one trough lining up with the next, one peak lining up with the next, one crest lining up with the next? Well, there probably is. There's probably a point up there that's much closer to the blue one than it is to the red one, point A. In fact, how much closer is it to the blue one than the red one? It's exactly one wavelength closer. In other words, for the blue one to get home, it's 15 wavelengths, but for the red one to get home, it's 16 wavelengths. And so what are we seeing? We're seeing that it's exactly one wavelength further for the red one to get there than the blue one, but they're still going to arrive beautifully lining up with each other. If they're beautifully lining up, thinking back to interference, what sort of interference is that? Beautifully lining up, in phase, crest to crest, trough to trough. Constructive interference. And that was exactly the same sort of interference we had at point X as well. But what about if we think about another point? One that's halfway in between that X, that central point, and the A, the one where they are meeting up also in phase. What about if we call it Q? One Q's alright, it's just when you've got four of them that it's a problem. Well, for the blue one, still exactly 15 wavelengths. But for the red one to get to that same point, it's no longer 16. It's 15 and a half. And so the path difference is half a wavelength. And that means that when the blue one arrives, the red one is going to arrive all muddled up. It's going to have its crests lined up with the troughs of the blue one, and its troughs lined up with the crests of the blue one. Thinking back to interference, what does that mean? That means destructive interference. I'm going to take a photo of this for you guys. And so, in fact, this is exactly what we see. If we shine light, red light, beautifully in phase, crest meets crest, trough meets trough. If we shine it at a set of double slits and then look at the pattern on a distant screen, we see exactly this. We see a bright spot right in the center, and we call that the central maxima. Sometimes we call it the zeroth maxima. And then on each side of that central maxima, we see a symmetrical pattern of other maxima spreading out from it, getting gradually less and less bright, and in between them, nothing. And so it's exactly like that. We've got our 0th maxima in the middle, and then on each side of it, the first maxima, then the second maxima, and the third maxima, and so on. It's not necessarily stopping there, but then in between. What's happening in between? That's those points of destructive interference. Minima, we call them. And so we end up with a pattern like that. And thinking about this is quite incredible, really, because how much is the wavelength of light? It's hundreds of nanometers, about half a micrometer, and there's 1,000 micrometers in a millimeter. And so when we're seeing a pattern like this, the difference in distance travelled by the light from the bottom slit compared to the top slit, well, at the central maxima it's 0. At the first maxima it's 1 wavelength. One lot of 500-ish nanometers. It's minuscule, absolutely minuscule. And so what we have to be really clear on is that path difference. If it's a maxima, it's going to be n lambda. And if it's a minima, it's going to be half a wavelength, 1.5 wavelengths, 2.5 wavelengths. How do we write that kind of algebraically? N minus a half wavelengths. Put in 1 for n, 1 minus a half, half. Put in 2 for n, 2 minus a half, 1.5. Put in 3 for n, 3 minus a half, 2.5. And so you're always getting the correct number of wavelengths. For a maxima, n lambda. For a minima, n minus a half lambda. And this doesn't just work with light, it works with sound too. Check out the link I'm going to send you. You can do this at home. Now don't go and hang up just yet, will you? There's more coming. So the bright fringes are what we call maxima, or antinodes, and they form when the path difference is equal to n lambda. That means the waves arrive in phase and cause constructive interference. While those dark fringes, which you can see on the picture as the little dark gaps between the red fringes, they're called minima, or nodes. They're caused by destructive interference when the two waves arrive 180 degrees, or half a wavelength out of phase, having had a path difference of n minus a half wavelengths.